Sorry, Gigi.
Yeah, we all do the same thing. Yeah.
Go ahead, read. What is the photoelectric effect? That's not the definition of photoelectric.
I literally just have a photoelectric effect.
No one wrote what it is.
You never had a frequency changes. Yeah. It's only like 2-3 pages.
We were just kind of saying stuff, and we were kind of writing down what we heard.
Wavelengths is what I wrote.
So when you get to college, you got to do a better job of writing down everything you don't know. What?
We're not in there.
You might as well be. This class is harder than a lot of freshman chemistry classes in college. You might as well be. All right, I'm going to explain it again. So if you don't really get this, what we're going to do today doesn't make any sense. Where the heck is it? The only reason, whatever, you want to call me a jerk, but when you're in college, they don't necessarily stop and say, did you write that down? Or do you understand that? They just talk, and they assume everyone understands things. So you have to, really make sure you're doing what you need to do.
College teaches you how to teach yourself. That's it.
Well, a lot of these professors love listening to themselves, even more than me.
Of course, I didn't pay
Lights,
the big
please.
bucks. Wouldn't you?
So,
I love listening to myself all day.
photoelectric effect is when a light is shined on a piece of metal. If it's a proper frequency and intensity, electrons will be ejected off of that metal. That is the photoelectric effect. So, when light, so for example here, what are we doing here? We're going to use, this is sodium, we're going to turn up the intensity, and we're going to use 403 nanometers. When light is shined on a piece of sodium, if this light has the proper frequency, it will give this metal the proper energy, and that energy will actually allow the electrons to jump off of the metal. The reason again, what is photoelectric effect? When a light shined on a piece of metal, ejects electrons from that metal. That's what it is. Why am I bringing this up now? Well, we spent a couple days talking about how the Bohr model is wrong. Why is it wrong? How's the Bohr model wrong?
All the shells are the same distance.
They're not. That's what Bohr said. Bohr said all the shells are equal distance apart. They're not. Who remembers what's the deal? You have the nucleus and the first level is really close to it. Then what?
The biggest difference is between 1 and 2.
There's a
and then
big
the
gap between 1 and 2, and then
2 and 3,
2 to 3, 3, 4, 5, 6. Those, they get really, really close together. And a lot of that has to do with that math I showed you in the Khan Academy video, and we didn't need to write all that down. But the point I was trying to show you is that if you measure, now if you look in your notes, you should have these numbers written down. Okay, so you have your n equals 1, then you have your n equals 2, and then 3, 4, 5, 6, 7, right? 3, 4, 5, 6, 7. This one is negative 13.6 electron volts. This one is negative 3.4, I want to say. You guys with me here?
Yeah.
Does this ring a bell? Negative 3.4 electron volts. Is this ringing a bell, I hope?
Yes.
Okay. This one. Yeah, that doesn't have the... Sorry, I wasn't planning on, I thought we were just going to kind of review this and then move on. I wasn't ready to do this. I thought I had a picture with all the...
We watched the video.
Yeah, no, but I thought I also had a... Hold on, let me just...
I don't think he went through all of them.
You watched the video.
There it is. That's what I'm looking for. Okay. Good enough. All right, so So yeah, n equals 3 is negative 1.5, and they get smaller. Okay? Negative 1.51. So the point is, the energy needed to eject an electron from this first level is way higher than to eject it from up here. Okay? So the whole point of this is, we already kind of talked about this. Now the nucleus is down here. The radius from the nucleus to this first level is very small. This is very big. Then they get more narrow up here. Okay? It should make sense to you that the further away you move, the less energy required to remove the electron because of the Coulombic force and all the stuff we've been learning, repulsion, shielding, all that jazz. Okay, now this photoelectric effect definitely has something to do with these these numbers here. There's two equations we're going to learn about. E equals hv and C equals lambda v. For you physics people, V is F, frequency. H is Planck's constant, E is energy in joules, C is the speed of light. Lambda is your wavelength. Remember, light moves like a wave. So, like this. Okay? Depending how long that wave is, alright, and how short the wave is, think of it that way, your wavelength gets bigger, your wavelength gets smaller. So frequency and wavelength are related, that if this wave is really big, so from essentially one peak to another, think of it that way. If I stretch this out, like a radio wave and microwave, radio waves are enormous, okay? A wavelength of radio wave could be like a football field, okay, one wavelength. But then all the way at the other end of the spectrum, ultraviolet cosmic rays, they're so squished together, wavelength is like, incredibly small, all right? And we'll have some numbers. Hello. What's up? Okay. Okay. Yeah, period 8. So, yeah, okay. Thanks. Bye. All right, so, in other words, this is a constant. What is that? Speed of light. 3 times 10 to the 8th meters per second, or 3e8 meters per second. So if your wavelength goes up, so we stretch that wave out, your frequency must go down to keep that constant. And if I squeeze the wave together, and I have really small wavelength, my frequency goes up. And remember, if I put something here, and we're timing how many of these peaks pass that line in 1 second, so if the line's traveling this way at the speed of light, all waves move at the same speed, the electromagnetic spectrum, all light moves the same speed in a vacuum when we assume we're in a vacuum. I know that's crazy, but that's how we do it. Then, however many peaks pass that in 1 second, that's called frequency, or hertz. Seconds to the -1, or hertz. All right, or 1 over seconds. The reason I'm going over all this right now is I'm trying to tie all this stuff we've learned into what we're doing in lab that we're going to start today. So you're going to learn how to use these equations. The frequency of this light, so the wavelength is 403 nanometers. You plug that in here, divide the speed of light by that, and it'll give you a frequency. So the frequency of this violet light that we're shining on sodium, it's a certain number. And that number, that frequency V, goes in here, multiply by h, which is Planck's constant. When you multiply them, you get a certain E. If that E is at least equivalent to one of these numbers, it can eject an electron. If that E is not equivalent to one of these numbers, the electron will not be ejected. That was the whole point of all of that. That this photoelectric effect directly dependent upon how much energy it requires to remove an electron from each energy level, which has been calculated, and I kind of showed you that. You don't need to explain all that. You just need to have a rough understanding of, okay, there's more energy closer to the nucleus. If we change the frequency, okay, go up to red. Now the wavelength lambda is 756. And by the way, this has to be meters, but you plug that in, and you get another frequency by using the speed of light. You plug that frequency in, guess what? E isn't high enough for any of the levels in sodium. So therefore, no electrons are ejected. So the lower the frequency, right? The lower the wavelength, That's going past violet towards ultraviolet. When you squeeze these wavelengths together, what happens is you're going to have a really, 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 really high frequency. So think about this. If this V gets enormous and this H is a constant, H times a really big number, you're going to get a big E, which means you can eject all types of electrons because you're reaching those numbers. And you're going, it's called the threshold frequency. If that frequency is the threshold frequency, meaning it has enough energy to eject electrons, this will happen. If it doesn't have enough energy, then it won't. And the intensity of light, all right, again, that affects it. That's a different factor, but essentially like how strong is the light. Not the frequency or wavelength, but how strong that light source is, right? So you don't need to know all the details. All I'm trying to get you to understand here is reviewing what the heck is this. This is when the light that you shine on metal has enough energy, electrons are ejected. That's what photoelectric effect is, all right? And you can actually measure that with a current. You set this up, it'll start generating electricity, and that's what this is all about. And that's how you can prove it's happening, because you can't see electrons, obviously. These two equations work together to explain something like this. Your lab that we're going to do, you're going to take diodes, LED lights of different colors, and you're going to be measuring voltage and wavelength. We're going to do it two different ways, and you're going to be calculating the energy. So kind of related to this, all right? So that was important to go back over that and explain why we learned all that already. Okay, lights please, Tristan. So now, again, Planck's quantum theory, those two equations, all right, E equals hv, all right, H is Planck's constant. Anybody from physics remember? 6.36 times 10 to the negative 34th joules seconds. You're close. That is a constant. V is frequency, which is kind of crazy because in physics it's a lowercase f, which it should be. It's more like, I think the V has like a little tail on it, one of those. Because V is velocity, but the like cursive V is frequency. And the unit on this is seconds to the minus 1. Or 1 over seconds. So if you multiply joule per second times seconds to the minus 1, which is 1 over seconds, your seconds cancel and then you get joules, which is E. So E is joules, so energy. E is energy in joules. This is how we figure out the energy on the energy levels, or the energy required to remove electrons or have them jump around. So if an electron goes from the first to second, this E in this equation is any energy associated with energy levels and electrons either coming off or going on. That's what you need to know, okay? Energy associated with the energy levels. Okay, I'll leave that up there. C equals lambda V. C, speed of light. Again, this is in a vacuum, but a lot of times in science, physics, and chemistry, we have to ignore things like friction and air resistance, which sounds crazy, but it's too hard to figure it out if you try to take all that into account. I don't know how to do it. So we assume we're in a vacuum. 3 times 10 to the 8th meters per second, 3.0. If you want to use your E, obviously, you know I don't care about that. Lambda is wavelength, but this needs to be in meters. A lot of the wavelengths in your book or online or in the lab or whatever, even on the wall back there, it's nanometers just because it helps put it in better perspective because the meters are so small. But we need to use meters, and here's why. Because this is meters per second, and lambda is meters, and frequency we just learned is seconds minus 1. So if you do meters times 1 over seconds, that gives you meters per second. So that's why it has to be meters. And then again, your frequency here is V, seconds to the minus 1. So the way these two are connected is the frequency. So the wavelength of light coming from these lights, coming from the sun, whatever source of light, a flashlight, those gas tubes that we looked at with the spectrometer or spectroscope. Okay, all this, anytime there's a source of light, you can measure the wavelength, which will you can calculate your frequency from that, And then you can plug it in here to say, okay, what's the energy associated with that wavelength of light? And that's what I'm trying to express here. That's what we're going to learn how to use these, interpret it, and make sense of it. The color of light, whether it's blue, green, red, yellow, violet, whatever, is directly dependent upon these calculations. So red light has a different wavelength than violet, which will result in a different amount of energy. So if I gave you the energy of a source of light, you should be able to work backwards and tell me what color that light is. That's what I'm getting at. So when you see these LEDs, and there's red ones and violet and blue and whatever, you should be able to say, okay, I know this is red, I can see it. Now does the numbers make sense? Because you match it up, you look it up online or in a book or back on the wall, and say, okay, that E, or that wavelength is associated with red light. So I did it right, everything's working out. All right? So we're going to use the lab to kind of learn how to do this. And we're going to start doing it right now. I'm not going to just give you notes on this because I think the lab's a good way to do it. So, I got like 2 markers going here. All right, here's what you guys need to do. Someone come up and grab these and pass them out. Wait a second. Did some of you take these already?
Yeah.
I was going to say, I only have 4 left, or 5. Everybody needs one of these. These are the questions to your lab. I didn't copy the lab, but that's all right. I can tell you how to set it up. You're going to do this with me. So everybody come up and grab these. All right.